Sure. So for anyone who's not aware, this is a talk I'm giving tomorrow to the School of Mathematics and Statistics, and it's a slide talk, so I'm going to give it as I'll give it tomorrow, which means I won't be writing on the boards or anything like that. So in this talk, I'm going to talk to you about differentiation, division, and the bicategory of Landau-Ginzburg models, which is what my thesis was called on this same topic. Let's get into it. So what did I do in my thesis? So I provided some additional exposition on something called the theory of bicategory of the bicategory of Landau-Ginzburg models. So currently, a lot of the literature on this thing is fairly technical and inaccessible to non-experts. So my thesis goes some way to make that a bit more accessible. As I was doing this, I also isolated some techniques from the literature on the bicategory of Landau-Ginzburg models, which might prove useful in other contexts. So in particular, I looked at the construction of an explicit homotopy equivalence between a causal complex and its homology. And then I also simplified this technique under some natural conditions. And we'll get to exactly what that looks like a bit later in the talk. But this simplification avoids passing to the completion of a ring. And it involves constructing a generalization of partial differentiation, which is based on polynomial division. So that's where we're gonna start things off. So if we take a look at the next slide, I'll ask you to consider the question of, can you differentiate with respect to an arbitrary sequence of polynomials? So throughout this talk, let K be a field and consider a multivariate polynomial ring over K. And how might we go about defining differentiation in this polynomial ring with respect to the variables squared, so the polynomials x1 squared through xm squared? Well, given a polynomial f, we could write this in the following form. So as a sum of powers of these polynomials, so a sum of powers of xi squared, where the coefficients in this sum are polynomials that don't contain any terms involving something that looks like xi squared, right? And then we could go ahead and just define differentiation as you would for using the usual sort of power rule. So looking at the power of xi squared as it appears in that expression for f, decreasing it by 1 and multiplying by the power, as you do with differentiation. So, for example, in a two-variable polynomial ring, and this polynomial f equals y plus z squared plus yz squared plus y squared z cubed, then we can write f in this form, right? So we have f as a sum of powers of the variable squared. In this case, all the powers are 1. And then in this case, under this sort of quasi-definition, the differential of f with respect to y squared would be z cubed, and the differential of f with respect to z squared would be y plus 1 plus zy squared. Okay? So the question is, of course, how do we actually generalize this and make sure that this is a definition that actually is well defined and makes sense? And for that, we're going to exploit a link between differentiation and polynomial division. So for the purpose of this example, let's just consider a one-variable polynomial ring. And what we can do is we can pass to the polynomial ring in two variables. And in this polynomial ring, we have the following identity, right? So on the right-hand side, although there's the infinity at the top of the sum there, this is a finite sum, because eventually that the nth differential of f will be 0. And I think this is fairly clearly inspired by something like Taylor's theorem, and this is not too hard to prove. Now the point is that when we rearrange this expression, so bringing the 0th term of that sum to the left-hand side, and separating out the first term of that sum, we obtain an expression that looks like this. And what that says is that the differential of f as a polynomial in y is the remainder of f of x minus f of y divided by the polynomial x minus y squared, right? So this is what we're basing our generalization of differentiation on. Okay, so let's take a look at the next slides. In order to make this definition, we need to recall some concepts related to polynomial division. So we'll go back to our multivariate polynomial ring. And in this polynomial ring, we have a division algorithm. So what that says is, given a polynomial in this ring and a sequence of polynomials t1 through tn, then we have an algorithm which produces polynomials r and q1 through qn, which satisfy the following equation, along with some other additional defining properties. And what we do is we call r the, as you might expect, the remainder of f divided by the sequence t. And what we're going to do is we're going to consider the set of possible remainders of division by a fixed sequence t, and we'll call this, in this case, c of t, right? So that's every polynomial in Kx which arises as a remainder of division by t. It's not too hard to show that this is a k-linear subspace of Kx. Okay, so we're now ready to make our general definition. So we're gonna fix some terminology. So we're going to pass to the polynomial ring kxy, where we have the original variables x1 through xm, and then copies of those variables, which we call y1 through ym. And we're going to fix a sequence t in kx, which satisfies certain conditions. And these are going to be the polynomials which we are going to be differentiating with respect to. Given this sequence t, we're going to look at the sequence of differences of these polynomials. So ti as a polynomial in x, subtracted from that ti as a polynomial in y, and then we're going to look at the sequence of these differences. So this sequence of capital T's here, what we're interested in, a factor of our definition will be the space of remainders of division by this sequence of differences. So C of capital T as a subspace of KXY. So T satisfies, this little sequence T satisfies certain conditions. The point of these conditions, which I won't bother stating, is that the following lemma holds, is that every polynomial f in KXY can be written uniquely in the following form, right? Where we have f written as a sum of powers of these difference polynomials, where the coefficients in this sum are remainders of division by big T, right? And of course, that finitely many of these are non-zero. So the right-hand side is actually genuinely a sum. Okay. And then from here, we're ready to make our definition of generalized derivatives. So given a polynomial f in Kx, we're going to let rho u of f denote the polynomial which is a remainder of division by t. We're going to let that polynomial be the unique polynomials which satisfy the following expression. So if we take a look at the lemma on the previous slide, every polynomial has unique polynomials Ru, which satisfy that expression. And then for taking capital F equal to little f of x minus f of y, we'll just let Ru of f denote that particular polynomial, which is guaranteed to exist uniquely by that lemma. Given all that, we'll define the derivative of f with respect to t as the coefficient of ti in that expression, where we look at that coefficient polynomial and we identify the xi variables with the yi variables. So that's what phi is doing. Phi is mapping from kxy to kx, and it's identifying xi with yi. And this rho ei of f is just the coefficient of the polynomial capital Ti. Okay, so to get an idea of what's going on here, let's take a look at the following example. So if you're following along closely, this is the same example that we had from the very start of this talk. So we'll look at a two-variable polynomial ring and the sequence of squares of the variables. And then we'll look at the polynomial f equals w plus z squared plus wz squared plus w squared z cubed. And then we're going to pass to the ring where we duplicate each variable. So as well as w, we have w prime, and as well as z, we have z prime. And we're going to consider these differences. So in this case, t1 is w squared minus w prime squared, and t2 is z squared minus z prime squared. And I don't expect you to be able to check this now, but you can show that we can write f of wz minus w prime z squared in the following form, where we have this polynomial r, which isn't particularly important exactly what it is, and these following coefficients of the ti polynomials. Really, what we're interested in this expression for f, subtract f, so f of zw minus f of w prime z prime, are the coefficients of t1 and t2. So the coefficient of t1 is z prime squared, which is our row e1 of f, and the coefficient of t2 is w plus z w prime squared plus 1, right? And then to compute the differential, we just look at these polynomials and we map z prime to z and w prime to w, and we find that the differential of f with respect to w squared is z cubed, and the differential of f with respect to z squared is w plus wz squared plus 1. And if you're following very closely, you'll notice that that is the same thing that we got right at the start. Okay. So now let's move on and talk about some of the properties of these polynomials. So if you'll go over to these boards here, what we can do is, so if we look at this this board here, we have the following properties. So first of all, this operation, this thing I'm calling differentiation, it satisfies the property that we would expect, the power law property we would expect, right? So for a product of the polynomials ti, if we differentiate with respect to ti, this product with respect to ti, then we reduce the power of ti in that product by 1, and we just multiply by that power. I forgot to draw this up, but so r here is a remainder of division by t. And these remainders of division by little t act like constants with respect to this operation, meaning we can pull them out of this differentiation map as shown there. And also, as we would definitely hope for, it is a k-linear map. Now, from these three properties, which sort of, I guess, justify it being called differentiation, you can show the following things. So that the common kernel of all of these maps is just the set of remainders of division by t. And due to our conditions on t, which I haven't told you, this is isomorphic as a k-module to kx mod t. And also from those properties in the previous theorem, you can show that Ti satisfies some version of the Leibniz rule. Now, we got onto this whole sort of generalization thing by discussing Taylor's theorem. And the following theorem is a version, I guess, of Taylor's theorem for these maps. So what it says is that if we differentiate f with respect to a whole bunch of the Ti's, possibly multiple times, then this is the same thing as looking at the corresponding coefficient in the series expansion for f that was used to define this map, except that we also need to chuck that map phi in there, which is identifying the variables x and y, and of course multiply it by the corresponding sort of power factor, so v factorial there. And if t were the variables, right? So not regular polynomials, but t were the variables. And so we did have our version of Taylor's theorem here. Then we could write down exactly the same thing and remove the map phi, and we would have equality as polynomials in the y variables here. Okay, so what does this have to do with the bicategory of Landau-Ginzburg models? I've talked about differentiation, I've talked about division. So what's this stuff about the bicategory of Landau-Ginzburg models? Well, first of all, what even is the bicategory of Landau-Ginzburg models? So it's a bicategory of a certain type of polynomial singularity. Its objects are pairs. One of the things in the pair is a polynomial ring, multivariate, and the other thing in the pair is a polynomial in that polynomial ring. And it's a special type of polynomial called a potential. And when k is the complex numbers, then these potentials are exactly the polynomials which have isolated critical points. Okay. The one morphisms in this bicategory are these objects called matrix factorisations. And so before we discuss this more, we need to discuss a little bit about what on earth a matrix factorisation is. So if we take a look at that, we can think about a matrix factorisation as being a Z2 graded kx free kx module x together with an odd differential, which is a lot of words, but you can write that data like this, right? So you have two parts of x, x0 and x1, with dx mapping between x0 and x1. And the whole point of this is that this differential squares to multiplication by u, right? This polynomial u. You can think about matrix factorizations in exactly the same way as chain complexes, with two key differences. So they are Z2 graded rather than being Z graded. And their differential squares to something which is non-zero rather than squaring to zero. If we take a quick example, right, we have a polynomial u equals x squared minus y squared. Then the following thing is a matrix factorization of u. So the point being is that these two matrices in this sort of diagram, when we multiply those matrices together in either order, we get u, the polynomial u times the identity matrix. Okay. And we don't really have the time to go into, all the properties of matrix factorizations, but many concepts from the world of chain complexes transfer to the world of matrix factorizations. So the notion of a morphism of matrix factorizations, it's just a linear map which commutes with the differential. And likewise, we can define things like homotopy and homotopy equivalence in a very similar way to chain complexes. The point being is that the relevant category of matrix factorizations is the homotopy category. So this is a fact that's been well established in the literature. And for our purposes, the important thing is that the homotopy category of matrix factorizations encodes a lot of information about the singularities of the thing we're factorizing. And what that means is that finding homotopy equivalences of matrix factorizations is an important task, right? Okay, we're going to look at one particular type of homotopy equivalence called a strong deformation retract. And you can make this definition either for complexes, as it is usually done, or for matrix factorizations. So a strong deformation retract consists of the following data. It has a map pi from y to x, where y and x are either matrix factorizations or complexes, and then a map back the other way, sigma, from x to y, right? And these maps form a homotopy equivalence in a particular way, such that sigma followed by pi is equal to the identity. So not just up to homotopy, it is actually equal to the identity. And then in the other direction, pi followed by sigma, that is the identity up to homotopy. And this homotopy, which relates pi sigma to the identity on y, must satisfy some additional properties. Now, the point of homotopy equivalences, of strong deformation retracts, is that they are susceptible to this technique called perturbation, which is a technique from homological algebra. Now, I won't go into the details of perturbation, but what perturbation does is it lets us modify certain types of homotopy equivalences like strong deformation retracts. So that's why we're interested in this particular type of homotopy equivalence. Okay, let's get back to LG. So in LG, we're going to consider some one morphisms. So we have what we've got in this diagram here. We've got some potentials U, V, and W, and then we've got a matrix factorization X and Y as acting as one morphisms between U and V and W. And it's possible to define a kind of tensor product for matrix factorizations. And this is the sort of device that's going to play the role of composition in the bicategory of Landau-Ginzburg models. Now, this is good, but composition is, in some sense, an infinite dimensional object. However, it always has some sort of finite dimensional representative, at least up to homotopy, right? So when we want to work with compositions in this bicategory, we want to be able to access what that finite dimensional representative is. And the tool we have for doing that is this thing called the cut operation, which is the whole reason we needed to introduce strong deformation retracts. So the cut operation is an explicit strong deformation retract between the following matrix factorizations. So on the left, we have this thing called the cut of X and Y. And all we need to know for this talk is that the cut of X and Y is this finite dimensional representative. All we need to know is it's in some sense finite. On the right, we have an exterior algebra tensored over K with the composition of X and Y. And if we think about, properties from commutative algebra, it's not too hard to see that this thing is really just a bunch of copies of the composition of X and Y with direct sum together, right? So this strong deformation retract relates a whole bunch of copies of X and Y, of the composition of X and Y, to something which is in some sense finite, right? The point of this cut operation isn't just that this strong deformation retract exists, it's that it's explicit, meaning we actually know how to compute all the maps involved. And this is important because we want to use the cut operation to compute compositions in the bicategory of Landau-Ginzburg models. Remembering we only care about these matrix factorizations up to homotopy. Particularly we only care about them up to homotopy. Okay, so now we're going to talk a little bit about how we go about constructing the cut. So we're going to start out with a system of our generalized derivatives. So that was the point of introducing them at the start of the talk for some sequence T. And then we're going to use that to construct a strong deformation retract involving something called the causal complex. We'll get to exactly what that looks like in just a sec. And then from there, we would use perturbation techniques. We won't have time to go into the details of this in this talk, but you would use the homological perturbation techniques to upgrade this causal strong deformation retract to the strong deformation retract, which forms the cut operation. Okay, let's take a look at the next slides. Oh, wait. Okay. So remember, these are our one morphisms. We're looking at their composition in LG. And we're going to let our sequence T, the sequence we're going to differentiate with respect to, be the sequence of the normal partial derivatives of the potential V, right? And we're going to suppose that we have these differential maps. So V being a potential implies some of the necessary conditions on T for these things to exist. And the other conditions are satisfied in many interesting examples. And we'll discuss this point a little bit more right at the end. We're now going to consider the causal complex of T. So the causal complex is a chain complex over KY, which is associated to the sequence T. And its underlying module is the exterior algebra on a free module of KY. I won't write down its differential, but what it consists of basically is multiplication by the elements of T and messing about with some wedge products. One important fact about potentials is that if V is a potential, then this causal complex we're interested in is exact except in degree 0. Now, this means that our goal is to produce the following strong deformation retract. So because this causal complex is exact in degree 0, its homology is just except in degree 0 is just ky mod t concentrated in degree 0. And we want to produce this strong deformation retract. So we're going to denote the generators of this causal complex by certain symbols dti. Now, these are just formal symbols. There's no particular technical reason for writing things this way, except that it's meant to make you think about differential geometry. So for a polynomial f in ky and a wedge product of these dti's, we think about, so omega being the wedge product of these dti's, we think about f omega as, which is an element of the causal complex, as being like a p form on affine n space, right? Now, in light of this, we define the following map, which we call a connection on the causal complex, as follows. So we look at this p form, f omega, and we differentiate with respect to t. We differentiate f with respect to t, and at the same time we wedge omega by the corresponding dti. And if you are somewhat familiar with stuff in differential topology or geometry, this might be reminding you of some things to do with the de Rham complex, and that's sort of roughly where these ideas sort of, I guess, come from. Okay, and then given this definition, after a fair bit of work, one can show that if the characteristic of K is 0, so K, the field we're working over, is 0, then we have the following strong deformation retract. So exactly the strong deformation retract we were looking for, where the homotopy is given in terms of the differential on the causal complex and this connection nabla. Of course, there's quite a bit to show in order to prove this statement. In particular, the inverse that I'm writing up, you need to show that that thing actually exists. But it is possible, and I do so in my thesis. So previously, before my thesis, this was only done in general over the t-adic completion of the ring ky, and it wasn't really clear when it was actually necessary to pass to this completion. Now, the conditions on T such that the differential maps exist, these also characterize the situation in which passing to the completion is not necessary. There's a little asterisk there because as I've set everything up in this talk, that's actually not true. But you can sort of define things in a different and similar way such that this statement becomes true. Okay, so why do we care about whether or not we need to pass to the completion? If we pass to the completion, then we can only compute this homotopy H up to t-adic approximation, right? If we have to pass to the completion for some reason. And why is this a problem? Well, let's think about why we're actually doing this. The whole point of coming up with this strong deformation retract is to do computations in the bicategory of Landau-Ginzburg models. And if we can only compute the homotopy up to t-adic approximation, it's not entirely clear how useful that is in doing your computations. Maybe it is, maybe it's not. But at least in the case that you do know things on the nose, everything is sort of working out as expected. Okay, in summary, what did we do? So we started out with a system of generalized derivatives. That's what we defined at the start. And then via a connection on the causal complex, we used this to define a strong deformation retract involving the causal complex. From here, we didn't do this, but from here, one would then use perturbation techniques to show, to produce the cut operation in LG. Cool. Thank you all for listening, and I'm happy to take any questions now.
Thanks, Rohan.
Cool.
So what do you do in characteristic P, Rohan?
Yeah, I don't know.
That's the typical math question. It's like you can always make somebody squirm by asking them, "What about characteristic P?"
Well, I guess, right, like in characteristic P, that commutator's not invertible. So I guess the answer is it doesn't work.
Yeah,
Maybe.
I don't know the answer. Yeah.
Yeah. I mean, you can still define the connection and everything, but yeah.
Yeah, I mean, there's probably there would be an appropriate modification. There's a concept called divided powers, which is a trick for. So somehow what you're doing here is to do with the fact that you kind of want to divide by factorials, right? So so when you divide the exponential, you take x to the p divided by p factorial. Well, in characteristic P, of course, you can't do that. But still, this combined operation, x goes to x to the p divided by p factorial, you can view this as a single unit. This is called a divided power, and you can do something with that. So, yeah, at some point I had well, if somebody forced me to care about characteristic P, I might redo this with divided powers, but so far that nobody succeeded in doing that. So
yeah, instead you spent your time doing it with non-Ethereum.
That's right. Yeah, you gotta pick your insanity. That's my flavor of insanity.
Yeah.
Any other questions for Rowan?
No.
Cool.
I guess. Let me see. What kind of question will you ask? Well, a typical question is, what next? Now, I know what's next, and it's probably not more of this, but suppose that you were to do more of this, what would be next?
Yeah, so I think like these differential maps are kind of interesting. And it would be sort of interesting to see whether they can, these ideas of sort of thinking about these things in differential geometry terms, whether that would go anywhere, whether that would be useful for anything else. I've got no idea whether it would, but it sort of seems like it should. Maybe not though. And yeah, I suppose, I mean, are you asking like personally or like sort of with this particular talk?
Well, yeah, I mean, in the context of your thesis, there's usually threads left unpulled and paths not taken. So, yeah, I think you answered my question, but usually, okay, stepping back a minute and taking off my audience hat, why does somebody ask this question? Well, they want to get a sense of, were you a puppet on a string, or were you engaged autonomously in doing this? And if you're engaged autonomously in doing it, you probably have generated thoughts about opinions about things, or to-dos to come back to. And so having at the ready a kind of, oh yeah, well, if I had another 6 months to think about this, I'd probably go check this idea out. Kind of is a tell that you were thinking about this at a certain level. So yeah, it's a good question to be able to answer.
I think actually what the best answer is to that would be like a better characterization of the conditions which those maps exist.
Yeah,
right.
That's a good answer.
Because because I don't know. I think because like there's those examples where it seems like they exist, but it doesn't fit into the conditions that I stated in my thesis. So, yeah, I don't know. And I don't exactly immediately see how to adapt that.
Yep. Yeah, but that's it.
So that'd be interesting.
Yeah. Okay, I think we'll leave it at that. Thanks, everyone. Thanks, Rohan, and good luck tomorrow.
Okay.